Okay. Okay, good afternoon, everyone. This is the second part of the tutorial on pulsars and radio astronomy. Yesterday we looked at the coordinates which are employed in astronomy and how the different coordinate systems are related to each other, and how do we locate the stars or the astronomical objects which we are trying to study. And we also had a look at the astronomical time and what role it plays in the observations. Okay. So I think the coordinate systems and the time are important aspect of doing any astronomical observations, not just pulsar observation, but any astronomical observations. Essentially, you need to know where the object which you are studying is located and when can you actually observe it and for how long can you observe it. Okay. So it was from that point of view, we had a look at it. But today I would try to move more towards the thing which I was going to talk about, which is the observations of one specific class of objects called pulsars. Okay. You have already had a lecture on pulsars, the full form of which is pulsating radio sources. And you probably have a fair bit of idea about what these objects are. Okay. So I'll go, maybe I will recap some of the things towards the second part of our tutorial today. But essentially, what we are going to focus today on is how do we actually uh, observe these sources? How do we investigate these sources and what kind of things which we can do with this? And what is the typical instruments which are sort of used in this? So to motivate this, yesterday we already started with a time series, which has been given by Desh and Prakash to you as part of a worksheet thing. Okay. And we had a look at that time series and we saw that it looked like a random noise. But there is a very strong pulsar, in fact, the strongest pulsar in the southern hemisphere, the Vela pulsar, which is hidden in that time series. Okay, so the question was to how to sort of extract that out. And uh, I already mentioned that it is the strongest pulsars. In radio astronomy, you must have done it in some other lecture. You characterize the brightness or the strength of a radio source by using a unit which is typically very, very small. And that unit is called Jansky in honor of the father of radio astronomy, Carl Gunther Jansky. And it's about 10 to the power minus 26 watts per meter square per hertz per steradian. So as you can see, 10 to the power minus 26 is a very small number, and typically pulsars are millijansky, so another 3 orders of magnitude weaker than that. So obviously, this pulsar is the strongest in the southern hemisphere. It is actually in Janskys, its flux density. But despite it being in Janskys, you are not able to see it in that time series. Okay. So there is some reason why you cannot see it. And to be able to extract that signal out, we need to massage that raw data, which, as we discussed yesterday, was the voltage data. And one way to pick out that signal is to take a fast Fourier transform, which will concentrate the power in the signal. And we discussed yesterday that pulsars they produce periodic radio emission. So it would concentrate the power in the frequency, in the fundamental of the signal, and maybe make it rise well above the noise, which again, as we discussed yesterday, is related to the noise in the time domain using the Parseval's theorem as far as the Fourier transform is concerned. Okay. So that is why we do the harmonic analysis, or we take the Fourier transform, which is part of your worksheet. Okay. But towards the end, I had asked another question that is not the only reason for doing a Fourier transform. There is another reason for doing a Fourier transform. That's where we had stopped. So now that you have had a whole night in between to think about it, does anyone have an answer to that question? Or any guesses? Okay. Guesses are also perfectly fine.
The phase,
Yeah. So somebody said phase yesterday also. So why phase is important?
because it indirectly will tell you how the pulsar signal is affected by the pulsar magnetosphere itself and the ISM as well.
Okay. So what you have said is partly true. Pulsar magnetosphere is not so much of an issue. But the other part which you said, and can you say the full form of the abbreviation which you use, the second
Uh,
part?
Interstellar medium and
Right. So,
ionization.
so why is interstellar medium important there?
The ISM has some natural frequency, right, of the oscillation of the plasma, and if we want to observe the pulsar at lower frequencies, then it affects the signal, like it makes some time delays in the signal, and from there, what to say, the factor of time delay, we can assume we can know the content of the ISM in our line of sight.
Right. Okay. So that's correct in the sense that uh, that is what happens in the ISM, and that's what this slide shows. So essentially, the medium between the pulsar and you is not vacuum. It has free electrons, a very small density of free electrons, but then the distance to the star is also very, very large. So if you look at the column density of the electrons, it's fairly large. And these electrons will get knocked around by the propagating electromagnetic wave. And in the process, they will extract energy from that and re-radiate the electromagnetic wave. Okay. And they do this in a collective behavior, which is called as cold plasma. So the net effect of all this is that your phase of the electromagnetic wave is affected, and it is affected in such a way that it is dependent on the frequency of observation. So if you are observing the pulsar at high frequency, let's say 5 gigahertz or 10 gigahertz, the amount of effect which happens is much smaller than when you are observing it at a lower frequency, which is, let's say, 300 megahertz or 100 megahertz. Okay. And that all follows from the dispersion relation in a cold plasma. Okay, so this is what at least the physics students must have done. Whoever has had a physics must be knowing about dispersion relations in plasma. So this dispersion relation is essentially the speed of the propagation of the electromagnetic wave as a function of frequency. Okay, and the group velocity of the electromagnetic wave reduces as you go down in the frequency, is goes down as nu to the power 2 or nu square. Okay. So the lower the frequency, the lower is the velocity of the propagating electromagnetic radiation. And since our pulse is an electromagnetic radiation, the lower speed implies that it arrives later. Okay. So there is an increasing delay with progressively decreasing frequency of observation, and that is given by the expression which is shown here. Okay, where you can see that for a small band of frequencies delta nu, it goes as nu to the power minus 3. Now, when this happens, then your pulse observed, suppose your telescope is observing over a wide range of frequencies. Let's say it is observing from 300 megahertz to a much larger range of frequencies. Okay. Like in this particular case, you can see that there is a wide range of frequencies, about 400 megahertz at L band. Then what will happen is that your pulse will come at different points of time. And the serration which you see there is the pulse. And the pulse is delayed more and more as you go down in the frequency. Now, if I add all this data together, I will see nothing because the pulse is there everywhere. So this dispersion essentially reduces the signal to noise ratio, which becomes very, very poor. And that is a issue. And this is just sort of telling you how the pulse signal will look like if you increase the bandwidth. So if you go from 1 megahertz to 4 megahertz to 8 megahertz, you will see that the signal to noise ratio is reduced. That is, here you see the pulse very clearly, but as we go down to larger bandwidths, the pulse becomes more and more smeared. Okay. And this is the problem which all the the data which you get from the telescope phases. Okay. Now, I hope I have convinced you that dispersion is important. So how do you take care of that? Any guesses?
By adding
So we break it
contribution.
up into harmonics and then sum them up.
Right. So if you have a large bandwidth, 100 megahertz or 200 megahertz, uh, the solution is here on these plots. So if, say, for example, if you had 8 megahertz bandwidth, if you had broken it down into 1 megahertz chunks, okay, you would not have seen so much of smearing. So the simplest solution is to break 8 megahertz into 8 1 megahertz chunk. This kind of breaking is called as filter banking. Okay. Now, does the FFT do that?
I guess the FFT works on the phase of the signal rather than breaking into the channels, right? The-
Now, what does the FFT do? So if you have 1024 time samples and you take a 1024 point FFT, what do you get?
frequency correspondences.
Yes, but these 512 frequencies, you're right. So 1024, as we discussed yesterday, the fast Fourier transform of a real signal has a Hermitian symmetry. So half the frequencies are unique. So you get 512 channels. But these 512 channels, are they same frequency or they are different frequencies?
Different frequencies.
And how do they map the entire bandwidth?
We have to convert them to the same frequency.
So let's say you had this 8 megahertz signal, right? Which is at the bottom plot. And you took a 8 point or 16 point FFT of this. So following the same math, we should get 8 channels. Now what these 8 channels will correspond to?
One for each
The
of the
first
bands.
half,
One,
the
two,
First, right. So first channel is going from what frequency to what frequency?
0 to 1 megahertz.
1. And second channel?
Then 1 to 2, 2 to
Correct.
3. That way.
Okay. So you have effectively, by taking the Fourier transform, you have effectively split the band into 8 channels. And you have done exactly what we wanted to do. That is, instead of having to look at the signal at one channel itself, you have now sort of split it up. Okay. And this is uh, the same FFT, which is doing the harmonic analysis, also does the filter bank. This is called a filter bank. Now, the advantage of this filter bank here is that your large bandwidth is now divided into several chunks. Okay. So, the output of that is a filter bank like this. Still, you need to do some other operation because your pulse is not coming at the same phase. So now comes the phase part of it. So the phase in each channel is going to be different because of the dispersion. So you have to do something to this phase to bring all the pulses together and then add it up, as somebody said earlier. So if you do that, then you will be able to recover the original pulsar. And this process is called as de-dispersion. Okay. So just remember that the Fourier transform gives you a filter bank. That filter bank allows you to divide a big bandwidth into a number of channels. And then you can do de-dispersion to obtain the original pulsar signal as it started from the star. So in the earlier days, when computers were not powerful, this was done by actually making electronics, which would divide the overall bandwidth into smaller chunks. It will subdivide the observational bandwidth into multiple channels. And one of the problems with this division is that your dispersion smear gets reduced, but it is still not completely eliminated because whatever subdivision you do, it will still leave you a channel with a finite bandwidth. And as we saw, delta T is proportional to delta nu in the earlier expression. So this finite bandwidth of channel would still mean that there is some smearing. So the number of channels which you want is a trade-off between the time resolution which you want and the size of the filter bank. And as I said earlier, it used to be analog filter banks. Nowadays, everywhere you use digital filter banks, which employ either the fast Fourier transform in hardware or fast Fourier transform in software. Okay. So for example, in GMRT in the earlier days, we used to have 256 channels over 16 megahertz, giving us a 62.5 kilohertz kind of bandwidth, which meant that from 32 millisecond, you could reduce the dispersion smear at a frequency of 300 megahertz to 110 microsecond for a reference DM. Okay, so you could see that dispersion smear could be significantly reduced, but still it would be of the order of few microseconds. So if you want a resolution, you needed a much larger number of channels to get a much better resolution. Okay, and this is just schematically showing what the FFT does. So you have the input band and it just splits it into a large number of channels. But as I said, there will always be some dispersion smear and that will limit your time resolution. Towards the end of the lecture, we will come across a investigation where one is trying to detect gravitational waves, and that requires a time resolution of the order of nanoseconds, not even microseconds. So such high time resolution data, simple filter banks cannot provide you. And apart from that gravitational wave detection, there are other studies, high precision astrometry, polarization studies, and tests of general theory of relativity, which require very high time resolution data. And again, the time resolution is a function of frequency, because remember that the dispersion relation is a strong function of frequency. As you go down in frequency, the dispersive effect of the medium becomes larger and larger. So for frequencies, low frequencies like the giant meter wave radio telescope frequencies, dispersion is a big nuisance. And to get high time resolution, you have to completely remove this dispersion. And you can actually do that. And that is done by using a filter which has a transfer function inverse to that of the interstellar medium. Okay. Now, this is something which the students with engineering background can understand much better, that essentially the interstellar medium is like a filter. It is like a unity amplitude phase delay filter. Essentially, it gives you the same amplitude, but it introduces a phase delay, which is a function of frequency. So if I want to completely remove this dispersion smear, I need to design an inverse filter to that, which will bring the phases all together. And that is a technique which is known as coherent dispersion. This has been employed in all high time resolution data. Okay. So the form or functional form of that inverse filter looks something like the expression which is given here. And it can, if need be, it can be completely implemented in software, which is what is done. Okay. Nowadays, we use general purpose graphical processing units, GPUs, to implement this entire signal processing in the software, where you have the input data coming, which is sampled at its Nyquist rate. And then you take a fast Fourier transform, which is a million, or in some cases, a billion point fast Fourier transform. And then you apply the filter function in the Fourier domain, and then take the inverse Fourier transform to get your high precision data. Okay. And the way it is implemented in high performance computers or GPUs is to do this FFT, because the 1 billion point FFT is very compute intensive. So you do this FFT by parallel processing. So a GPU unit has typically 1600 to 2500 streaming processors. So you can divide this into 1600 to 2000 different parts and do it in parallel computation. So eventually your input data rate and output data rate would match, and you will get a coherently de-dispersed data at all points of time. So this is a very important piece of equipment which is there in all radio telescopes nowadays for getting high resolution pulsar time series data. So yesterday when I was motivating the FFT, I wanted to sort of go here. I'll not go into the details because we don't have the time to go into the details. But if any one of you has any questions at this point of time, you are welcome to ask those questions. And before I move forwards, I would like to settle those questions. So, so I request, if just raise your hands if you have a question.
In this coherent dispersion mode, we don't have to again externally apply time delays, right? The FFT does it for you. Is it like that?
Agreed. So the inverse filter which I talked about applies that inverse delay. Okay. So as I said, the delay is a function of frequency because that's the nature of the ISM. So you have to apply an inverse delay, which is also a function of frequency. So in coherent dispersion, it does that. So you don't have to externally do anything else. Correct.
Okay. But
yeah, but just to, can I add something? Because I heard
sure.
Saying something in the part of the question. Just the FFT operation will not correct for these. FFT operation facilitates you to, get information finely sampled across frequency. Then you still have to apply for this correction explicitly before retrieving the sequence back by an inverse FFT.
Yeah. So in this block diagram, where there is a green block called chirp, that chirp is the filter, inverse filter, which is the core of this operation. Okay. So the FFT, the two FFT which you see in the two block diagrams are only convenience things, because the Fourier transform tells you that you can do filtering much more efficiently in frequency domain. Okay. You can computationally you can do the filtering much better in the frequency domain. So the FFT is just to go to that domain. In principle, you could have done this entire thing in the time domain also, but this is just a computationally efficient way of doing that. So FFT is not important there. The important thing there is the chirp function. So does that answer the question?
Yeah.
Yeah.
But
Any other? Yeah, go ahead.
We don't know the characteristics of the ISM in our line of sight, then we don't know the phase variation delay factor we want. So, I mean, for searching new pulsars, how can we proceed with not knowing the
Yeah.
ISM or the column density?
So searching new pulsars, this is a problem whether you do coherent dispersion or you do incoherent dispersion. Okay. The word coherent comes from the fact that here the phases are important. In incoherent, the phases are not important. So the previous filter bank which I talked about was incoherent. So both of those have a problem when you are looking for new pulsars. So for looking for new pulsars, what you do is you assume a large number of trial DMs, okay, and search for the pulsar for each DM. And that is why pulsar searches become even more computationally intensive, because you have to repeat this kind of a process as many times as many trial DMs you have. So suppose you are searching for 1,000 trial DMs, you will have to repeat your harmonic search 1,000 times, one time for each of the dispersion measure. So coherent dispersion is employed for pulsars with known DM, okay, not generally employed for pulsar searches.
Okay.
Any other questions? Okay, if not, so let's proceed further. Okay, so having given that basic introduction to the type of systems which we use for observing pulsars, let me go a little bit more in detail. And as far as this part is concerned, I will be actually moving a little faster than normal, because the details are something which one can discuss if you have interest on any of those details. I'll not go into the details. Okay. So we'll look at what are the different motivations of the pulsar observation, what kind of signs we are looking for, and then have a brief look at the instruments which are used, and then towards the end talk about what kind of data analysis is employed for doing this. Okay. So let's start with what is the kind of data which you are looking for. The simplest form of data is just to make an image of the pulsar. And why you would like to do make an image of the pulsar? You may want to make an image of the pulsar to get its position. Pulsars are high velocity objects, which means that they are moving at very high velocities. Some of them move at 1,000 kilometers per second. Okay, so which is a very large velocity. So they will actually move in the sky, and that is called proper motion. So if you make two images separated by a few years, you can actually see the pulsar in motion. You can find out the flux density of the pulsar. And if you find out the flux density of a pulsar at different frequencies, you can get the spectral index of pulsar. And all these are important quantities to measure if you want to understand why the pulsars are emitting the way they are emitting. And most important is that you can map the environment of the pulsar. Okay. And this requires narrow synthesized beams and multiple frequencies. And since pulsars are very weak sources, a very large telescope. Okay. So this is just an example of showing the sort of flux density of the, showing the, in one particular case, showing how the pulsar proper motions can be. Unfortunately, this has not come out very well. But essentially, with respect to the fixed background of the stars, you can actually see if the pulsar is moving around. Okay. This is another example where you have a fixed background of star and you can see the pulsar which is in the center is actually moving, and that motion, proper motion, you can work out for such sources. This is an example of mapping the environment of the pulsar. So you see a big nebula around the pulsar, And in fact, this is a full complex where you have several supernova remnants. It's called as Kukubura complex. And there are pulsars there. So you can actually study whether these pulsars have anything to do with its environment and how they are affecting their environment. So this is one motivation. In addition to that, most of the time, we are looking for high time resolution data. Okay? Angular resolution is not so much important because pulsars are very tiny compact sources. So they will just look like point sources. But the time resolution is important, especially for a class of pulsars which have millisecond periods and are known as millisecond pulsars. Okay? Again, you need a high time resolution instrumentation to actually do the science which you want to do. And you need a large telescope because pulsars are very, very weak radio sources. Okay. So these are some examples of high time resolution. This is a coherently dispersed data for the fastest or the second fastest pulsar 1937. And you can see that there's a huge, you can see a very clear structure, two pulse structure there. The time resolution here is 200 nanoseconds. Okay, so that's the kind of time resolution which one is talking about. Okay. Time resolution also becomes important in other studies where there is structure within the pulse. And this is an example of the giant pulse in Crab pulsar, where you can see not only the structure, but also the circular polarization in the pulsar. So time resolution is important, and we need instruments which can give you that time resolution and very large telescopes. Okay. Lastly, the spectra of the pulsars is important, and also how the pulse morphology changes as a function of frequency is important, because both these things give you handles on the mechanism by which the pulsars emit the radio emission. In addition to that, you can also measure the dispersion measure, which is also a proxy for the distance of the pulsar. Okay, so most of the pulsar distances are known via their dispersion measure, and we saw that the pulse arrives at different times at different frequency, and we can use that to actually get how much dispersion is taking place in the medium and study the interstellar medium. So basically use the pulsar as a shining light to illuminate the interstellar medium and study the characteristics of the interstellar medium. So this requires multiple frequency observations and a very high time resolution, as well as polarization, because pulsars are very highly polarized sources, some of them with 100% linear polarization and so on. Okay. So again, this is an example of how the pulsar pulse changes as a function of frequency, and you see that all kind of evolution takes place. So your double component can become triple components. The amplitudes of components can change as a function of frequency, and this is telling us something about the pulsar beam itself. Okay. And again, high time resolution can be used to test theories of relativity. It can be used to look at esoteric effects of general theory of relativity and so on. I'll not go into the details of that. I'm just illustrating the things. Since pulsars are highly polarized, measuring polarization is an important thing. And just as we had a coherent dispersion pipeline, which is giving us total intensity, you can actually also get 4 Stokes parameters coming out of that. And again, you need a very high time resolution as well as a large telescope to do this. Okay. And this is just some examples of that. So based on this motivation, a typical pulsar instrumentation requires the following thing. You need narrow synthesized beam, which means that you need an interferometer like GMRT spread over several kilometers, which will give you a beam size which is quite small. Say, for example, L band GMRT, the beam size is, you can get a few arc second kind of beam size. Remember, pulsars are point sources. You also need a telescope where you can observe the pulsar at different frequencies. So for example, at GMRT, you can observe it all the way from 150 megahertz to 1460 gigahertz. Telescopes such as Parkes radio telescope can go up to 10 gigahertz. And the now sort of destroyed Arecibo telescope could start from 300 and go all the way up to 10 to 15 gigahertz. GBT can also go even higher, up to 60, 70 gigahertz and so on. So the more the frequency coverage, the more is the information which you will get. Sampling rates have to be large, and the telescopes, since they are weak sources, your telescopes have to have large collecting area. So Arecibo is a very 300 meter, very large telescope. GMRT has a collecting area of roughly 47,000 square meters. Okay. Similarly, GBT has a fairly large collecting area. So these are the telescopes which are employed for pulsar observations. Okay. And you need special signal processing like coherent dispersion, which we discussed, and you need receivers which give you polarization. But most importantly, to be able to, as we will see later on, to be able to extract information from the pulsar time series, you need to time the pulsar. That means you need to find out the time at which a pulse arrives at your observatory, which is also known as time of arrival. Okay. To do that, you need a very accurate clock, and you need to associate the pulse with an accurate timestamp. So this is what you need for doing typically pulsar observations. And different ways you can have the data organized. You can have integrated profiles, which is essentially an average of a large number of pulses with timestamps. You can have full Stokes profiles like the ones which are shown here, where both the linear polarization and the circular polarization is indicated. And you can have dynamic spectra and high time resolution profiles. So these are the typical data products which you get from these instruments which we are talking about. Now, traditionally, pulsar astronomy was done with single dish radio telescopes, such as Arecibo or Parkes or Jodrell Bank or Effelsberg or GBT. And now the largest telescope in the world, which is in China, called FAST. So that is the traditional pulsar astronomy. And reason was that these dishes provided you a very large collecting area. But as time is going by and all the most modern telescopes, one realizes that to build a telescope which is as big as 100 meter or 300 meter or 500 meter is very difficult. So radio astronomy has moved towards synthesizing a large single dish using phased interferometers. Westerbork Observatory in Holland was an example of this. GMRT is another example. And the future telescope in the next 5 to 10 years, the square kilometer array, will have a square kilometer collecting area and would be made up of thousands of dishes, okay, which is again a phased interferometer. So there are both types of instruments which are used, single dishes as well as interferometers today. The interferometers are used by synthesizing a single dish, single equivalent dish. And that is done by phasing the individual dishes. So what is phasing? Phasing means that if you have a wavefront, electromagnetic wavefront, which is traveling towards your telescope, okay, it will arrive with certain delay at different telescopes in very simple terms. Okay, I don't want to go into mathematics here. So it will arrive with a different delay at each of the telescope. If you can find out this delay and compensate for this delay, then all your dishes, which are independent of each other and which are geographically located in different directions, at each of these telescopes, you will see the same wavefront. So if you could compensate for this phase delay, then you can actually add the voltages from each of the telescope. And such a combination is called as a phased array. Now, there are some things which are very easily, there's some part of the phase which is very easily determined. Okay. So for example, depending on the altitude of the source, you can actually work out what is the geometrical delay between each of the telescopes, okay, which is shown by this part here. Okay, so this right triangle, if you have the two telescopes separated by this distance, okay, you know that this much is the extra path length which the electromagnetic wave is traveling. And given the wavelength, there will be an associated phase delay. And this will be a function of the angle from the horizon or altitude. So basically, if you go up, if the source is right above you, then this delay will be 0, and this delay will change as a function of the altitude. So, and it's a geometric relation, so you can exactly calculate this and you can compensate for that. But there are other delays which are not so easily calculatable. For example, the signal from each of the telescope will be brought by cables to some central processing area. The delay in the cable can vary. It is sensitive to temperature, it is sensitive to various other factors. So it need not be fixed, it could vary a little bit. Similarly, the ionosphere will introduce its own delay, which can also vary, particularly at lower frequency and particularly at latitudes where India is, on the equatorial latitudes. Ionosphere can be a big nuisance. Okay. So what you do is you actually look at a source and determine these phases and then apply these phases. And this process is known as phasing. So in a telescope interferometer like GMRT, or say very large array VLA, or in future in square kilometer array, this is the procedure which will be employed to phase all the antennas together and thus form a synthesized equivalent dish. Okay, and that is also known as a coherent array, because here the phases have been taken into account. You could also do another thing, that instead of phasing the dishes, you could just take the voltage from each telescope, square it and get the power and add all of the powers together. The process of squaring essentially makes you lose the phase information. So now you are not taking phases into account. So this kind of a sum is called as incoherent sum. Both of these are employed in pulsar observations. The incoherent sum is less sensitive because you are losing the phase information, whereas the coherent sum is much more sensitive. And again, I'll not go into the details unless somebody asks me the question. But essentially, you can see weaker pulsars with a phased array than the incoherent sum. But in the incoherent sum, you can see a larger part of the sky as compared to the phased array sum. So both of them have their own advantages and disadvantages. And in an interferometer like GMRT, we apply both of these for doing pulsar observations. So this is just a typical schematic of how the antennas can be combined together. Again, I'll not go into the details of that, but you can add all of them after squaring, that is after converting voltage to power, and that is called as incoherent array output. Or you could add the voltages directly after compensating for the phase delays, and that is called as a phased array or the coherent sum output. Okay. So this I have already sort of, so this is an example of how you do the phasing. So before, so here each point or each symbol is the data from one of the GMRT telescope, and what is plotted on the y-axis is the phase in degrees, and what is plotted on the x-axis is the Indian Standard Time. So in the evening this observation has been taken. So you can see that the phase of each of the antenna is different. And then you look at a calibrator, find out how much is the difference, and then you compensate for it, and all the phases have come together. So if you are adding voltages here, you will get an output which will be very small, depending on the plus and minus sign of the phase. The output can even be 0. Okay. Whereas here, when you add all the voltages, you are now getting a phasor sum. So you will get a net output, which is like n times the number, where n is the number of dishes. Okay. So this is just illustrating the phasing procedure in, say, GMRT. I will not speak much about polarimeters, but you can also get 4 Stokes parameters from the voltage data from a phased array by doing appropriate processing. But most importantly, you need to time these signals. As I said, you need to time the period. So this is done by employing an atomic standard. In GMRT, we employ a set of 3 rubidium clocks and 1 hydrogen maser, which are 1 part in 13 and 1 part in 15 stable. So these are extremely stable atomic clocks. And the time is calculated on the basis of these atomic clocks. And the arrival time of the pulse is time stamped by doing a time transfer from this atomic clock to the actual observed data. And as we'll see, that is very important for experiments such as detection of gravitational waves. Okay, so this is all about the instrumentation. So again, I will like to pause here and see if there are anything which you would like to ask on this. As I said, I have not gone into the details. I've just given you a flavor. If any of you is interested in detail of any of those aspects, you are welcome to ask me now, and I will go into greater detail if there is interest in that. So please raise your hands and ask your questions. Yes,
Sir,
Sarvesh.
sir, can you please comment about the maximum detection value of GMRT, like in Jesse per beam?
So, so the sensitivity of a telescope or the detection limit of the telescope is given by an equation called radiometer equation, which I presume must have been covered in a lecture earlier. Okay, unfortunately I don't have the expression here, but the noise which you see at the output of a radio telescope is essentially proportional, inversely proportional to the square root of the bandwidth, and is also inversely proportional to the total time for which you have made the observation. Okay, so it's inversely proportional to the square root of the product of bandwidth and time. Okay, that is what is called as the radiometer equation, which I presume must have been done in one of the earlier lectures.
Yes.
So the larger is the bandwidth, the smaller is the detection limit. The larger is the time for which you observe, the smaller is the detection limit. And it also depends on how much noise your electronics introduces in your observation. Okay, so it's directly proportional to the amount of noise which your electronics introduces, and that is called as T receiver or receiver temperature. Okay. In addition, there is another factor which is the brightness of the sky itself. So although you are looking at a point source like Pulsar, you are seeing this point source in the backdrop of the background of the radio emission from diffuse radio emission from the sky. Okay. And at radio wavelengths, the sky, and especially in the direction of the galactic plane, is fairly bright. So that brightness also contributes to the noise which you get. And that brightness picked up by your telescope is called as antenna temperature. So the receiver temperature and antenna temperature, sum of that is your total noise. This noise divided by the square root of b tau will give you the minimum amount of noise which you cannot eliminate. Okay. And maybe 3 times or 5 times this noise is the signal which you can detect. Okay. Now, in the case of a incoherent array sum, you are looking at noise not from just one telescope, but from a combination of telescopes. So in the case of GMRT, let's say you're looking at 16 or 30 telescopes. So this number of telescope also goes in the denominator in that product of bandwidth and integration time. So your sensitivity is now inversely proportional to the square root of the product of the number of telescope, the bandwidth, and the integration time. Okay, so the larger the number of telescopes, the smaller is your output noise level. Okay, in the case of coherent array, your noise goes down as inverse of the number of telescope, not the square root of the number of telescopes. So the difference between the incoherent and phased array is by a factor of square root of n. Okay, that is why I said that if you want to see very weak pulsars, you generally employ a phased array, whereas brighter pulsars can be seen with an incoherent array. So have I answered your question?
Yes, sir. Sir, actually, you like said that we can't measure the value like beyond 3 times the sensitivity. So like uh, we can measure, but like we won't be confident that it's the signal or the noise, right?
Well,
Like it's
so
related to 2 sigma, 3 sigma, and all those stuffs, right?
yeah, so 3 times is 3 sigma.
Yeah.
Okay. So yes, in radio astronomy, usually we go, so for pulsars, we go 8 times, 8 sigma. Okay.
Okay.
Till 8 sigma, we don't really consider it as a good pulsar candidate. But 3 sigma gives you 95% confidence.
Sir,
So if you are X-ray astronomer, you would be happy with 3 sigma. Okay. So see, 3 sigma, 5 sigma, 8 sigma is just the confidence limit. If you, again, somebody must have covered this in the statistics part of this in one of the previous lectures. So if you look, if you assume the noise to be Gaussian random, the 1 sigma, 2 sigma, 3 sigma, they correspond to different levels, 67%, 92%, 95%, 99% probability that this particular sample is a part of the noise or not a part of the noise. Okay. So it's a question of how much confident you want to be. And in science, it's not that you have to take 5 sigma or you have to take 8 sigma. You could take 3 sigma as long as you have stated your assumption that I am only considering up to 95% confidence limit. So it's a perfectly valid scientific statement. But
May I
you are
add
right.
something to this?
Yes. Yes, Desh.
Yeah, since this question keeps coming up, it might be useful to state the variation of the thresholds in terms of standard deviation that we apply in different contexts. The general rule of thumb is the following, that if you have certain sequence of numbers or measurements, you ask what is the probability that any variation that you see, the peak variation that you saw, is a chance coincidence, chance realization of the noise process. And if you have 1,000,000 points, then you ask what is the chance that 1 in 1,000,000 point will exceed certain threshold, certain times standard deviation. And then you would like to avoid being cheated by such fluctuations. So you say, I will believe that something is a significant deviation only if it is above a threshold where the probability of the noise fluctuation giving me even 1 point above this is low. Okay. Or on the average, I expect maximum 1 point to exceed this, or less than 1 point to exceed this threshold. And so you will find this directly relates to the data size you're looking at. When you have few number of points, you might find 2 or 3 sigma thresholds might work very well, because the chance of 1 of the 100 points exceeding certain threshold, okay, is lower than 1. So essentially you ask for a cumulative probability in the probability density distribution, such a way that above that threshold, the integral of the probability density function times the number of points is less than unity. And this is how you choose your thresholds. And the reference that Balchan made about, for pulsars, we use more often than not 8 sigma or even higher than that. It is because we are dealing with large number of samples there. We are dealing with millions of samples for which 1 in 1,000,000 probability of exceeding certain threshold, okay, takes you to a very high threshold. Thank you.
Yeah. Now, just to add to Desh, so there is also another angle as far as pulsar threshold is concerned, and that is the man-made radio signals, which is also known as radio frequency interference. Okay. So the radio frequency interference generally will be an outlier to the system temperatures normal distribution curve. Okay. So when you are looking at a pulsar signal, when you are finding a new pulsar, you want to be sure that this is not a man-made signal. This is a signal which has come from the sky. Okay. So if you do a statistical analysis, you would find that between 3 sigma to 6 sigma, you will have a large share of the RFI, and RFI is a reality of the day because the radio astronomers work in an age of radio communication, mobiles, various other type of devices. So between 3 to sigma, you can be invariably sure that majority of your so-called pulsars are man-made radio frequency interference signals. Okay. So in pulsars nowadays, people go to very high threshold, and so as they said, it is also it is a function of the amount of data which you have, as well as in the case of pulsars, a function of the man-made RFI signals, which create a lot of problem. On the other hand, if you talk of X-ray in say high energies, in X-rays or in gamma rays, the number of photons which you get in gamma rays is very small. Okay, and so you have a sample out of which you have to work out the population distribution of the, or you have to work out the population statistics. So you make an assumption that this is a fairly good estimate. And again, at high frequencies, at gamma rays and so on, you don't have RFI of that kind. Okay. So given both these factors, a 3 sigma detection of a pulsar in gamma ray is acceptable. But in radio wavelengths, a 3 sigma detection of the pulsar is usually not acceptable. Okay. So it depends on the context. Does that answer the question?
Yes, sir. Thank you, sir.
Okay. Any other questions on instrumentation? Yes. Yeah, please go ahead.
Actually, my question is, how can you differentiate between, you can detect a celestial body such as a pulsar, but how can you differentiate this body and actually astronomical events such as a collision? If you have a pulsar and it collides against a black hole, it will emit radio waves. And how can you differentiate these waves from the collision from the waves emitted by the pulsar itself?
Good. So that's a good question. So while you have asked it specifically in the context of pulsars, this is true for any astronomical event. How do you say with certainty that this astronomical event has this explanation? Okay. So I would both answer it in terms of a particular context of pulsars as well as in a general context. Okay. So it's just the mere detection of radio emission is not the guarantee that it is a pulsar. Okay. The radio emission can come from hundreds of objects. It can come from extragalactic objects, from galaxies, from faraway galaxies, as well as from other type of stars and so on. So what you are looking for is something which is characteristics of the pulsar. And Devabrati must have told you in the lecture on pulsars that pulsars are rotating, highly magnetized neutron stars, which emit through from all the emission comes from the vicinity of their poles, from the magnetosphere. Okay, so if it has to be a pulsar, it has to be a periodic pulsating emission. That means you will see an emission, flash of emission, and then nothing, then a flash of emission, and so on. Okay, so periodicity is an essential characteristic to say that this is a pulsar. Okay. Also, the pulse emission mechanism studies, now about 2,900 of these objects have been discovered. So studying these objects, people have established that if you measure the flux of this object at say high frequency, let's say at 10 gigahertz and 5 gigahertz, that flux will be much, much smaller than if you measure it at a lower frequency. Let us say 300 megahertz or 500 megahertz. Okay. So the flux density or the brightness of the pulsar increases as you go down in the frequency. Okay. And this inverted spectrum is what is known as a non-thermal spectrum. That is, it is not a black body spectrum. If you look at a black body spectrum, it will go in the opposite direction. This is very different from the black body spectrum. So it's a non-thermal spectrum, and there is a typical physical process which would produce this kind of a spectrum. So when you see a pulsed emission, then you will say, okay, let me go and measure this pulse emission at different frequencies and see whether its spectrum matches with that of the pulsar. Okay. So if you have established these two parts, you are reasonably sure that it is a pulsar, but you could look at other aspects also. Okay. And essentially, the process of identifying an astronomical radio signal requires a series of checks and a series of elimination. And in the second part of the tutorial, if I come to that, I will explain how pulsars were initially thought to be neutron stars. Okay, that was a process of elimination followed by Jocelyn Bell and Professor Anthony Hewish to tie down these completely unknown signals to elusive but very well known neutron stars. Okay. So that's the typical process in astronomy, astrophysics, and science which you follow to identify a new object. In the case of pulsar, there is another thing that if you keep measuring their period, the period will not remain constant. It actually slows down. And that slowing down is essentially at the expense of the energy which the pulsar is losing. If it is, say, a collision or some other kind of a process, that slowing down will not happen. The slowing down is telling you that the star is losing its rotational kinetic energy. Okay. So there are these plausibility arguments which you make to say that I am reasonably confident that this is a pulsar. In the example which you talked about, which is neutron star colliding with a black hole, okay, when a neutron star and black hole merger takes place, first of all, you will get gravitational waves. Okay. So you should have a terrestrial detector detecting that gravitational wave. The second thing is that the electromagnetic radiation which you will get in that case will not be pulsed, and it will have a spectrum which is very different than the spectrum which we are talking about pulsars. Okay. It would be what is known as a hypernova. Okay. So the kind of thing which you will get in a collision like that, or a merger of a neutron star and a black hole, will be very, very different than what we have. We haven't seen a merger like that so far, although there are two cases now detected by LIGO, which could be very good candidates for this, but no confirmed candidate of a neutron star black hole merger has been seen. Okay. But so that was specific to your question. But in general, any new signal which you see in radio astronomy has to satisfy certain plausibility arguments. So the astrophysicist will argue with some specific reason based on the astrophysics he knows what would be the nature of this object. Okay. And sometimes you don't know for a long, long time. So gamma ray burst, GRBs, discovered in 90s, people did not have an idea about what kind of things these are till early 2000 and so on. And even now, the short gamma ray bursts, there is no clear-cut model. Okay. And we have radio signals now known as fast radio bursts or FRBs. And nobody has an idea what is the underlying mechanism which produces FRBs. Okay. So sometimes you can apply the known astrophysics to determine the nature of the object. Sometimes you don't know. You have to keep studying till you find the right cause or the right explanation for that kind of an emission. Does that explain the question? Or the,
yes.
Does that, yeah, okay.
Thank you.
Okay, so I guess since the most of the question, yeah, please go ahead. Yes.
Sir, I have just one question. So
yes.
if we consider a pulsar, so at once the pole which is facing towards us, it will come, then the other time the other pole will come towards us. So basically you would see two kinds of pulses, right? So so how can we differentiate like that?
So this is something which I also don't know the answer, because none of the pulsar astronomers know the answer. So first of all, in most cases, you see only one beam. Okay. So you most likely are not seeing the other pole at all. Okay. It's the geometry of your line of sight and the magnetic field and the axis which sort of determines that. In many pulsars, you see interpulsars, but you can explain them all coming from one pole, okay? Because the tilt between the rotation axis and the magnetic axis is so small that you can actually produce two pulses coming from the same poles. What you would need to discriminate between one pole versus two pole hypothesis is polarization information. And since I don't know whether this was covered in the lecture earlier or not, there is a typical polarization signature which a pulsar gives. That is the position angle of the linear polarization shows a S-type curve, which is because of the dipolar nature of the magnetic field lines. And you could actually use that to determine the geometry of the pulsar. And depending on this information, you could say whether it is coming from one pole or from both the poles and so on. But there is no clear-cut answer. I don't think there is a consensus on one pole versus two pole hypothesis as far as radio pulsars are concerned. Desh, you want to add something?
Yeah, I want to add two things. One is, since you might be referring to the lecture on pulsars, probably as far as I understand, it has not happened yet. It might be due in the coming days. Okay.
Oh, okay. Okay. I thought Devarvati has already taken a lecture on pulsars. Okay.
As far as, unless I have missed it, it doesn't
Monday
happen.
morning, Desh. You're right. Yeah.
Right. Okay.
Okay. So this is a problem then, because then I am assuming that everybody knows about pulsars.
No, Dipankar mentioned it briefly during his radiation processes. So the basic structure, I think it's.
Okay, then I should actually skip this part and, well, okay, let me quickly finish the data analysis and then go to, I have something on pulsars. So, although not great details, I thought that my pulsar material is more of a recap, but from what you tell me now, it will become the first introduction, which is a bit of a problem. But so let me finish the data analysis and then move to the pulsar part straight away.
It might actually help the students anyway.
Yeah. No, so I have very brief actually. I didn't, I assumed that everything has been discussed. So I have not actually, that's why I'm rushing through. So pardon me, all the students, because I am assuming that you know everything about pulsars, which I did not know. Okay, so let's move with the data analysis part, which is very quick and I can finish that. So as I said, the pulse arrives at different frequencies at different times. And if you want to have high signal to noise ratio observation of the pulsar, you need to de-disperse the data. Okay. So this process of de-dispersion is schematically shown here, where the x-axis is the pulse phase and the y-axis in the top plot is the radio frequency. So as you see the pulse is delayed progressively as a function of frequency. Now, if you want to recover the signal to noise ratio, you need to align this pulse, which means that the higher frequencies you have to shift backwards, and the amount of shift will depend on the frequency. So this shifting and aligning the pulse, this process is known as de-dispersion. And we have already talked about two ways of doing this. One way in which you just take the filter bank powers, where the phase information is lost. So that is called as incoherent de-dispersion. The incoherent de-dispersion is very fast, but it has the problem that your time resolution is compromised to some extent because there is a residual dispersion smear in that. The other method which we looked at it completely removes the dispersion smear, and it's called coherent de-dispersion, which also we saw earlier. The advantage there is that you can get very high time resolution data. So there are two ways of doing this analysis. In the earlier days, this was all done offline. That is, you recorded the voltages or powers and then did this in software offline. Okay. Today, all the pulsar instrumentation, this is done real time and online. Okay. So now we don't do this processing offline. The data which you get is already de-dispersed data. Okay. So, but if you are looking at older data, you may have to do it yourself. In addition to that, so this is for the known pulsars, because as somebody asked, we need to know the dispersion measure. Whereas if you want to find a completely new pulsar, then you have to search for this pulsar. And a typical pulsar search is a 5-parameter search. where two of the parameters are positional parameters, the right ascension and declination. And the other three parameters relate to the pulsar itself. The fifth one is the dispersion measure, which is basically the dispersion delay by the ISM, which is also a proxy of the distance to the pulsar. And then the period and period derivative of the pulsar. Okay. So, so typical, again, I'll not go into the detail. Typical analysis first tries to remove the man-made radio frequency interference as best as we can. Then de-disperse the data. So, okay, so let's go parameter by parameter. So the first two parameters, that is RA and DEC, that you find out by dividing your sky into a large number of pointings or small chunks. Okay. So if you have 100 square degree sky and your telescope beam width is 1 square degree, you will divide this sky into 100 points and then point your telescope to each of these points for a certain time, acquire the data, then go to the next point and the next point and so on, okay, till you have completed the entire survey. Okay. The center point of each of these beams will have a RA and DEC. And if you detect a pulsar in a given pointing, you know that its approximate position is that RA and DEC. So that is the first part of the survey. The remaining three parameters, P, P dot and DM, they are found by analyzing the pulsar data for a given pointing, where you already now know the RA and DEC. Okay. So DM, since we don't know, as I said earlier, you will assume a large number of trial DMs. So you will start from 0 and go up to a certain DM and divide it into so many number of trial DMs. And you will process the time series for each of the DMs. Okay. And once you have de-dispersed the time series for a given DM, then you will do a harmonic analysis to determine its period and period derivative. Okay. So, so essentially, this is how the de-dispersion is done for trial DM, DM0 to DM7. And each of this time series is then Fourier transformed, and then you look in the harmonic domain to find out the periodic signal if it exists, and then you reconstruct this periodic signal. So this is the typical way the pulsar search is sort of carried out. Again, details you can ask me later on. Okay. So once you have searched a new pulsar, then you look at this pulsar and then you try to derive its parameters. And the majority of the information about the pulsar comes from timing its pulse, okay, where you associate a time of arrival at the solar system barycenter to their integrated profile. So you pick up a point on the profile, okay, and this profile is obtained by averaging several thousands of periods, because individual pulses of the pulsars, they vary, they fluctuate. But when you add 1,000 or 2,000 of them, you get a very stable curve. And this stable curve is almost like a signature of that pulsar. So you associate some point here as the fiducial point, and you find out when this point arrived, and that is called as time of arrival. Once you have found out the time of arrival of a given observation, you come back after, say, 1 day and observe the pulsar again and find out the time of arrival, and you keep doing this for several days. Okay, and that is what is shown in this lower plot, where you have the x-axis in modified Julian days, and y-axis is the pulse phase residual. Okay, so this time of arrival, what you get from the actual observation is called as observed time of arrival. Then what you do is you know that the pulse is being emitted by virtue of the rotation of the star. So you make a rotational model of the star. You say that the rotational frequency of the star is omega, and this frequency is changing as omega dot. So this is the simplest rotational model of the pulsar. Okay. So given this, some assumed value of this rotational model, you predict a time of arrival of the pulsar. And you compare your predicted time of arrival with the observed time of arrival and find the difference between the two. The difference between the two is called as phase residual or timing residual. If your model is correct, then you will find that your phase residuals are all 0. But if your model is not correct, then you will find a systematic in your phase residual. So for example, if your frequency which you have assumed of rotation of the star is smaller than the actual frequency of rotation of the star, then you will see that your phase residual will monotonically increase, like in this particular plot. Okay, and how much it increases as a function of day will tell you what is the correction which you have to apply to get the actual frequency of rotation. This technique is known as pulsar timing, and it's a very powerful technique for extracting not only the motion of the pulsar, but also its position to a large degree of accuracy, its proper motion. If the pulsar is a binary, you can find out this, you can use this technique to find out the masses of the pulsar and so on and so forth. So this is where the most of the work as far as the pulsar data analysis is concerned is there. Okay. Again, if you are interested, I can go into the details, but not otherwise. So if your model is perfect, this is how you should see your phase residuals. If your frequency and frequency derivative are not correct, then you should see a parabolic curve like this. If your pulsar position is not correct, you should see a sinusoidal variation like this. If your pulsar is moving in the sky, has a proper motion, then you not only see a sinusoidal, you see a growing sinusoidal, and you can use, you can fit these residuals and get the values of period derivative, position, proper motion, and so on and so forth. Okay. So I think I will stop this here and then move to the next part of my talk. But before I do that, maybe I'll just give a 3 minutes break for questions and take few questions on this part. Now I will be moving on gravitational waves, where I will actually talk a little bit about pulsars. So before I do that, if anyone has questions on any of these parts, you are welcome to ask.
Sir, I had a small query. Is there any direct relationship between the period of rotation of a pulsar and the spectra of the pulses which we receive? Because we were analyzing the ORT data and we obtained something like that.
What do you mean by spectra? Spectra, you mean the Fourier transform?
Yeah, sorry, exactly, the Fourier transform.
Yeah. No, the word spectra has a different connotation in in astronomy. Okay, spectra is basically brightness as a function of frequency. Okay, so don't use the word spectra there.
Okay, sir.
Because that will confuse people. But I understand what you are asking for. Yeah, obviously, because you are using the harmonic analysis to find the period. So there has to be a relationship there. So the answer to your question is yes. Because all you are doing is you are taking a Fourier transform of your time series and then looking at the time series in the Fourier domain. So you are collecting the power in the periodicity of the pulse signal in time into one frequency bin. Inverse of that frequency is the period of the pulsar. So there is a Fourier transform relationship.
Yeah, there are two kinds of spectra. One is when you take the raw time sequence and Fourier transform, you will get the radio frequency spectrum. And then when you take the intensity and study that as a function of time, we generally refer to that as a fluctuation spectrum, in which you will see the harmonics of the pulsar signal.
Any other questions? Okay, if not, so my second part was supposed to be only 10 minutes, but it may become slightly longer. So I hope it is okay, Sykes and Prakash, because I was assuming that everybody knows about pulsars. So I may now take a slightly longer time than normal. Is that okay? We are already at 3:25. Okay. So I had kept it very minimal, but maybe I can spend more time in this entire thing. Okay. So the next part is more about the science. So what we were talking just now is how to observe pulsars. The next part is more about science. And since you have not had so my idea there was more question, answer and interactive. But since you have not been exposed to radio pulsars, so it would now become a little bit of more lecture kind of a thing. I hope that's okay. So I'll share my screen. Okay. Can everybody see my screen?
Yes, sir.
Yes.
Okay. So this is how a pulsar sounds in actual practice. That is, if you take a radio signal and then convert it to sound, you will hear a pulsar exactly like this. Okay. So the pulsars were first discovered almost 50 years back, 53 years back. And they were discovered not because somebody was looking for it, but they were discovered serendipitously.
Decision. We can't hear you.
Okay. So nobody, hello.
Yeah, Bisij, your audio was we couldn't hear you for a while.
Where did you lose me?
Yeah, from the beginning of this slide.
Where you said this was a serendipitous discovery. After that, we didn't hear you.
I guess we lost him. So. Maybe we'll wait for a while.
Yeah, sorry, I got disconnected for a short while. Can everybody hear me now?
We can hear you.
Yeah, when did you lose me?
So, like you said, accidentally it was discovered. So.
Okay, great.
This was a good example of a null that you're going to talk about.
well, I probably may not get time to go there, but yeah, that's true. Okay, so let me share again. Okay. Pulsars were discovered not because anybody was looking for it, but they got discovered by accident. And what Professor Anthony Hewish, who went on to get a Nobel Prize later on, was doing was he was looking at twinkling of radio stars, or what is also known as scintillation of radio stars, using a method called interplanetary scintillation. Okay. And he did this using a telescope near Cambridge. And the difference in his experiment from other radio astronomy, or for that matter astronomy experiment, was that you were recording the data at a very high time resolution. Okay. Typically in astronomy, you collect the data over minutes and in many cases over hours. And that's how you operate. But since he wanted to look for twinkling, he wanted to sample the data every millisecond. And that was the novel feature of his experiment. And the reason why I thought I'll spend some time on this was just to tell you that new discoveries happen when you open up a new parameter space. Okay. So if you have an instrument which is different from the instruments which have been built so far, you are sure to have a discovery. It may not be the discovery which you wanted, but it could be some discovery which is equally important. And in the MRAO Mullard Radio Astronomy Observatory telescope, which was a huge telescope spread over 4 acres, the novelty was sampling at milliseconds. And this was needed for studying twinkling and scintillations, because when you look at stars from your naked eyes, you can see that the stars twinkle at that kind of a time scale. Okay. So they were studying this, and then they accidentally happened to discover the periodic signals And this is just the plot from the discovery chart recorder. And again, I can spend a little bit of time because you didn't have radio pulsar lecture. This is also related to the question which was asked earlier. How do you know that this is a neutron star? Okay. So the first thing which Jocelyn Bell, Dame Jocelyn Bell, but in those times, the student Jocelyn Bell sort of found out was that the pulse signal came one third of a second apart. That is, she could see individual pulses which were one third of a second apart. And not only that, daily observations with this telescope showed that this pulse signal came 3 minutes 56 seconds earlier every day. And in yesterday's lecture, we had seen that the time of the star, if you take the sidereal day, it is smaller than the solar day by 3 minutes and 56 seconds. Okay. So it clearly told Jocelyn Bell and Anthony Hewish that this is a signal coming from the sky. Okay. More importantly, it had a width of the order of milliseconds. Okay. And if you imply a simple argument that any thing which produces an emission which has a width of an order of a millisecond should have a dimension which is sort of related to millisecond multiplied by speed of light. Okay. And if you do that, you can work that out. 3 into 10 to the power 8 meters to 10 to the power minus 3. Okay. So it should not be more than 30,000 meters. It should not be very, very large. Okay. So it has to come from a very compact object. More important, the period was not constant and the period kept changing as a function of time. So, and you could actually model the change of the period. And you could actually work out how much energy, if this change of period represented a loss of energy, how much energy this particular source was losing. Okay, which sort of tallied with the energy which a star of this type would lose. Last but not the least, they saw the effect of dispersion. That is, they had a band of frequencies at 80 megahertz. So they saw that the pulse at the highest frequency came earlier and the pulse at the lower frequency came much later. Okay. Which meant that this was a signal not in our in the Earth's atmosphere. This was not a signal in our solar system, but this was a signal which was way beyond our solar system. So it had to be some star. Okay. Either it had to be some star or it had to be the little green men or the extraterrestrial intelligence. But the extraterrestrial intelligence was soon ruled out when they discovered 2 more of these pulsars, which were very, very far away in different parts of the sky. So you would generally not have extraterrestrial intelligence from different parts of the galaxy. Okay. So obviously, this could not have been the little green men or the extraterrestrial intelligence, and it had to be an astrophysical source. So you see the reasoning which was employed by Anthony Hewish and Jocelyn Bell. They collected data, they characterized the data in terms of the characteristics of the signal, and then one by one ruled out different scenarios for doing this. They already knew that it has to be a compact object. So Anthony Hewish went to his library and checked which are the astronomical objects which are very small. And there were only 2 of them, white dwarf and neutron stars. Both of them were very well known. White dwarfs well known for more than 100 years before the discovery. And neutron stars known for about 35 or 40 years before. So they sort of tried to see, given the distance of this object, which was indicated by the dispersion measure, and given the periodicity and the slowing down of this object, whether either the white dwarf or the neutron star fits the model. Okay. And they used a series of arguments, which I don't know whether I have put it here. Well, I didn't put it here, but they used a series of arguments to sort of eliminate the white dwarf hypothesis, which left you with only 3 ways a neutron star can produce the signal. A neutron star going around another body can produce a periodic signal. A neutron star rotating around itself can produce a signal. So out of these, the discovery of the Crab pulsar in 1969 with a 33 millisecond completely ruled out the binary scenario of this entire thing, and they were left with only one possibility, which that this could be nothing but a rotating neutron star. The magnetized part came later, but the rotating neutron star part they were able to very reasonably argue in their landmark paper in 1968 in Nature. Okay. So what I wanted to stress here was that when you discover a new source in radio astronomy or in astrophysics, okay, the nature of that radio source is identified by a series of plausibility arguments. And in those arguments, you first generate different possibilities, and then you eliminate one by one different possibilities, which in the end will leave you with only one possibility, which would be true. And today, of course, after the discovery of about 2,900 of these objects, we know it very well that these are rotating magnetized neutron stars. Okay. So this was very briefly about the discovery of the pulsars. These are the two people who are credited with this discovery, Dame Jocelyn Bell Burner and Sir Anthony Hewish, who also received a Nobel Prize for the discovery of this particular pulsar. So very briefly, pulsars are highly magnetized rotating neutron stars. And these are the pulses, single pulses from a pulsar. As you can see, they are very periodic. Okay. So they emit a train of very narrow, highly periodic pulses with the periods ranging from 1.4 to 23 seconds. And the emission is what is depicted in this cartoon. So you have two beams of emission coming out from the poles. And every time the beam of emission cuts your line of sight, you see a pulse. Okay. There are about 2,900 of these known as of today. So they are like celestial lighthouses. Okay. Of course, all this Devabrati is going to cover later on in the lecture. So I just wanted to give the vital statistics of the pulsars. Majority of the pulsars are discovered in our own galaxy, Milky Way. Okay. This number is much higher now, 2,900. This is an older slide of mine. The periods, they are very, very stable, and they range over orders of magnitudes. So the fastest pulsar rotates at 700 times a second. It is 1.4 millisecond period. Whereas the slowest pulsar has a period of 23.5 seconds. So you have a 3 orders of magnitude variation in the periods of these pulsar. The pulsar period is not constant. It slowly increases, 1 part in 15. Okay. And it increases in a predictable way. So they are excellent clocks because of this reason. The radiation which we receive is coherent and is highly polarized with both linear and circular polarization seen. And they are steep spectrum sources. That means they are brighter at the lower frequencies below 1 gigahertz. And low frequencies is a very good frequency regime to study these sources. And that is why GMRT plays a very important role as far as pulsar astronomy is concerned, because the GMRT frequencies are from 150 megahertz to about 1460 megahertz. We have already seen that the pulsar signal is dispersed, but apart from dispersion, the pulsars also scintillate or twinkle, and their pulses are scatter broadened. Okay, and these 3 properties make pulsars very useful probe of ionized interstellar medium. Okay, they are very compact stars, 10 kilometers in diameter, with almost nuclear densities, 10 to the power 14 gram per centimeter cube, and a very high moment of inertia, about 10 to the power 45 grams centimeter squares, and so on. They are highly magnetized with magnetic fields ranging between 10 to the power 9 Gauss in millisecond pulsars to 10 to the power 15 Gauss in the case of highly magnetized pulsars known as magnetars. Okay. So in many respects, if you see, it's a star of extremes, and this extreme nature of these objects makes them very useful in doing experiments in fundamental physics. Okay. there are large number of interesting pulsars, and I have just listed some of them. The first pulsar which we talked about was 1919 plus 21. The fastest pulsar, the second fastest is 1.57 millisecond, but the fastest pulsar is now about 1.3 millisecond. The slowest pulsar is about 23.5 seconds. The first pulsar which goes around another neutron star was discovered in 1975, which also earned a Nobel Prize. It's called Hull-Stellar pulsar in 1913 plus 16. And you have found planets. In fact, the first exoplanets are found around a pulsar, which is 1257 plus 12. And then there is a unique system in which there are two neutron stars going around each other, and both of them are seen as radio pulsars, which is this J0737 minus 3039 and so on. This number is slightly older. As of today, 2,900 of these pulsars have been discovered. Majority of them long period pulsars of the order of a second, but about 300 odd pulsars are pulsars with millisecond periods, which are very important. And these are known as millisecond pulsars. The magnetic fields, as I said, range from 10 to the power 7 to 10 to the power 15 Gauss. Okay, so very large magnetic fields and so on. The most massive pulsar discovered so far is this pulsar 0740 plus 6620 with about 2.1 times the mass of the sun and so on. So this was just a brief introduction, and just to sort of indicate to you that the discoveries have not stopped. And the first pulsar was discovered in 1967 here, but you can see that from this cumulative distribution that the rate of discovery has actually not slowed down, which happens in many fields. It is actually becoming exponentially large. And we have discovered so many of the interesting systems in the last 53 years or so of the pulsar astronomy. Okay. So that brings me, I won't go into the other aspects of the pulsar, which I presume Devabrati will concentrate on. I just wanted to sort of refer to one part of the science which can be done, and that is the gravitational waves. I will come to gravitational wave in a while, but I will first motivate why pulsars are important for gravitational waves. They are very massive and they are very compact. And this massive and compact nature of pulsar implies that they have very precise rotation. The rotation is remarkably stable, which means they are almost like a clock, okay? Like the clock which we wear. In fact, in 1990s, pulsars were thought to be even better than atomic clocks. That is not the case now, but there was a time when International Astronomical Union thought of making clocks based on pulsars. The stability is 1 part in 100 quintillion, which is fairly stable. And because of this clock-like nature, they play a very important role in detection of gravitational waves. So we will look at pulsars as an instrument of detecting gravitational waves in a little while. Okay, and you look for gravitational wave by timing the pulsar. This is what I have explained to you earlier, what is pulsar timing, but I thought I'll just schematically show in an animation how pulsar timing looks like. Okay, so the red pulse here is the observed pulse phase. That is, you point your telescope to a pulsar. The pulses as they come, you associate a time of arrival of the pulse, observed pulse, and that is what is shown by the red pulses which you see here. And then you assume a model for the pulsar rotation and other pulsar parameters. Okay, and here is a case where the pulsar is a binary pulsar. That is, the pulsar is going around another star. So since it's going around another star, the pulse frequency is suffering from Doppler shift. When the pulsar moves towards you, the frequency increases. When it moves away from you, there is a redshift in the frequency. So if you have a good model of the binary system, you can actually predict the pulsar coming. Okay, so in this case, we have not assumed any binary system. We have only assumed a simple rotation. Okay, so you see that your modeled pulse, which is denoted by blue in color, is not matching with your observed pulse, which is red in color. Okay, and there appears to be a difference in time of arrival between the red and blue. which is what is plotted as a function of time in the lower plot. So this is the phase difference or the phase residual or the timing residual. Okay? And you see that because of the binarity of the pulsar, this phase residual or timing residual is actually having a sinusoidal kind of a behavior. If I can fit this sinusoidal behavior with a Keplerian model, I can extract all the binary parameters of this pulsar. Okay. So pulsar timing, which I explained earlier also, is a very powerful technique of extracting information from a pulsar system. And it is this technique which evolves, which enables us to detect gravitational waves, as I will sort of explain a little later. We have already discussed the effect of the of the ionized interstellar medium, that you have dispersion. But apart from dispersion, the ionized medium also leads to the scintillation and scattering. And both the dispersion, scintillation, and scattering can lead to a change in the time of arrival of the pulse, which is something which one needs to take into account if you want to do a very high precision measurement of time of arrival. So for the gravitational wave experiment, one would like to measure this time of arrival to few nanosecond precision. Okay, but dispersion alone will make your time resolution poorer than that. And in addition to dispersion, if you have scatter broadening, and I'll show an example later on, that will further degrade your time resolution. So we need to understand the effect of the ionized interstellar medium to a large extent before we can do a high precision timing of a particular pulsar. So it is a nuisance, but to sort of compensate for that or to take that into account, what one needs is to do the observations of these pulsars at lower frequencies. Okay, and what better telescope to do this than the upgraded giant meter wave radio telescope, because the upgraded UGMRT has a frequency range from 150 megahertz to 1460 megahertz. That is exactly the range where these propagation effects are very dominant. We have already seen dispersion goes as nu to the power -2. The scatter broadening goes as nu to the power -4. It's even a stronger function of frequency than the dispersion. So if you want to characterize these effects and then take them into account for high precision timing, you need a telescope like GMRT. So that was the point which I just wanted to make before we go into the entire thing. Okay, so this is just about scatter broadening, and scatter broadening happens because of multiple path propagation of the pulsar signal, which leads to producing fringes as well as time delays. The fringes lead to scintillation, whereas the time delay leads to broadening of the pulse. I'll again not go into the details of this. Okay, so these things, the clock-like nature allows you to use pulsars as tools for detecting gravity waves, which is what I'll come to in the last 3 or 4 of my slides. Okay, so what are gravitational waves? Gravitational waves were unique distinguishing features of general theory of relativity. Okay, so it's a natural consequence of the way Einstein proposed general theory of relativity that gravitational waves exist. Okay? And he himself was confused about this for a time, but eventually he wrote a paper in 1918 in which he proposed that natural consequence of general theory of relativity would be gravitational waves. And these gravitational waves were first detected again using pulsars in the Hull-Stellar pulsar, which I mentioned earlier, 1913 plus 16. But that detection was not a direct detection. There, the orbit of the binary system was shrinking, and the loss of energy of the binary, if you equate it to the gravitational wave radiation, the loss and the radiation matched exactly. And that allowed Joseph Taylor and Hulse to infer that in that particular system, gravitational wave radiation is taking place. Okay, and for that discovery, they were given a Nobel Prize. Okay, however, this discovery was not direct. it was an indirect inference from a pulsar timing measurement of the Hulse-Taylor binary system. So you needed a direct detection, and up to 2015, there was no direct detection, although there were terrestrial detectors which were trying to look for it. But in 2015, eventually, these gravitational waves were discovered. Again, I don't have time to go into the details of gravitational wave. I think somebody must be covering it in the school. But essentially, the gravitational waves lead to stretching and shrinking of the space-time. And like electromagnetic waves, they also have two polarizations. This is what is known as a this is what is known as a plus polarization, and this is what is known as a cross polarization. And your space and time shrinks and stretches in this particular way when a gravitational wave passes through the space-time near you. Okay? And the amplitude of the gravitational wave is the dimensionless ratio between the stretch of a particular length. Okay, so if you have a detector which is which has a length of L, this detector will shrink or stretch by delta L when there is a gravitational wave with an amplitude of and given by a characteristic strain H is passing through this detector. Okay. Now, this number is very, very tiny. For high frequency gravitational waves, this is of the order of 10 to the power minus 18 to 10 to the power minus 21, depending on the source. Okay. The typical nuclear dimension is 10 to the power minus 15. So it was a very hard thing to detect. And there were gravitational wave detectors operating in US, which is known as LIGO, which tried to detect this for almost 15 to 20 years and failed. But they kept on working on it, and eventually in 2015, they detected a source, and this is just the detection plot of that particular source, which was detected by the Hanford and the Livingston LIGO detectors. Okay. This was the first direct detection of the gravitational waves, but these gravitational waves were high frequency. In the sense, if you look at the frequency, look at the lowermost plot here, the y-axis is frequency. The typical frequency of this gravitational wave varied from 64 hertz to 256 hertz, which is in the gravitational wave astronomy called as high frequency regime. Okay? And these gravitational waves were produced by merger of two black holes, which were of masses 30 times and 35 times the mass of the sun. So during the merger phase, they radiate gravitational waves very strongly. And during the merger, since the binary orbit is shrinking, the frequency of the gravitational wave also increases. And you get a signal like this, which is known as a chirp signal. Okay? Typically with a frequency, depending on the masses, of the order of tens of hertz. Okay? So this detection opened a completely new field in astronomy, where electromagnetic waves are not involved. Okay? So these are now gravity waves, and this field in the last 5 years has developed quite a lot. So while these waves were high frequency, you also have a full spectrum of gravitational waves. Just as the electromagnetic spectrum extends from radio waves to gamma rays and higher frequencies, similarly, the gravitational wave spectrum also extends from ultra low frequency gravitational waves to high frequencies. So this was the high frequency spectrum of the gravitational waves. But if you want to detect nanohertz level of frequency, which is called as low frequency, then you have to use a different method. What would produce a nanohertz frequency? A nanohertz frequency will be again produced by black holes, but now black holes which are supermassive black holes. Okay? Black holes which don't have a mass of 30 or 100 or 200 times the mass of the sun, but black holes with 100 million to billion solar masses. Where are these black holes? These black holes are there in the centers of the galaxy. For example, in the center of Milky Way galaxy, we have a very massive, supermassive black hole system. And if two galaxies, they collide with each other, it is quite likely that the black holes of each of the galaxy will become gravitationally bound, and they will go around each other as a binary system. And such systems are known as supermassive black hole binary systems. Okay. One candidate example of this is the system known as OJ287, which has a 12-year orbit. The assumption is that it has a 12 years orbit, and it has two black holes. One is 150 million solar masses, and the other one is 18 billion solar masses. And both the black holes go around each other. So when you have a system like that, they will produce gravitational waves, just like the ordinary black hole binaries produce gravitational waves. But the frequency of this gravitational wave will be related to its orbital period. And as I said, the orbital period here is 12 years. So if you take the inverse of 12 years, you will end up at a frequency which is in nanohertz. Okay. So if you want to detect, if you are interested in nanohertz gravitational waves, your sources are supermassive black hole binary systems. Okay. Now, in the history of the universe, after the universe was formed, because of many such mergers, one expects a large number of supermassive black hole binary systems. Each of them will produce a gravitational wave, which would mean hello, am I audible?
We lost you for a little while, but now you're audible.
Okay, okay. Now I am audible, right? When did I get lost?
Yeah, we're close to 4 o'clock, so maybe one should round up in a short while.
Yeah. I should actually sort of finish this up quickly. Okay, so this kind of a gravitational waves, if you want to detect, you have to detect it using pulsars, and that is what the pulsar experiment is all about. Okay. So I will probably end with this. I will just probably end with this particular animation here to show you how schematically pulsar timing arrays can detect gravitational waves. So I will leave this as the last part of the entire. So is the animation visible?
Yeah,
hello,
visible.
Yeah. Okay. So these are the two supermassive black hole binaries. Now they have two supermassive black holes, which have now been, after the merger, become binary, and they are producing gravitational waves in some faraway galaxies. Okay. And these gravitational waves are propagating in space-time. The green lines are the space-time. So they come from a faraway galaxy. They reach our Milky Way. And inside the Milky Way, you have pulsars. So as the gravitational wave goes between you and the pulsar frequency changes with blue shift and red shift, which is what the color is denoting here. And that blue shift and red shift can be detected by pulsar timing, which I said earlier. Okay. Now the frequency of this will be nanohertz. So you will see a slow variation in the timing residuals over a period of 10 to 12 years or 15 years. So if you have not just one pulsar like in this case, but you have an ensemble of pulsars, many pulsars in many directions, then you should see a correlated signal in each of these pulsars. And that correlated signal can be used to infer a passing gravitational waves. Okay. So that, in very brief, is the principle on which what is known as pulsar timing array experiment works. And in India, with GMRT, we are conducting an experiment which is known as Indian Pulsar Timing Array Experiment, which is a part of an international experiment. There are 3 other experiments going on abroad, one in America known as Nanograph, one in Australia known as Sparks Pulsar Timing Array Experiment, one in Europe known as European Pulsar Timing Array Experiment. So our experiment, together with these experiments, combine our data in an international experiment known as International Pulsar Timing Array Experiment. And the hope is that by monitoring about 60 to 90 of these pulsars, we would detect these gravitational waves. In fact, we are coming fairly close to it. It's quite possible that in the next 3 to 4 years, we have a positive detection of these nano frequency gravitational waves. So I will stop here, and it's already 4. So I don't know how many questions people would want to ask, but if there are any questions, you're welcome.
Excuse me, sir.
Yeah.
Sir, one of my teammate had a couple of questions. He isn't here right now because he had some other class to attend. So he sent me the questions. So I'm just gonna ask that so he can catch it up later.
Sure.
So he asks why gravitational wave energy falls as 1 by r.
You mean to say why it propagates as 1 by r? What do you mean by falls as 1 by r?
I'm not sure, like that's how he sent me the question. So I couldn't even clarify that with him.
Yeah. So see, gravitational radiation is analogous to the electromagnetic radiation, except for one fact, that it is quadrupolar in nature. Okay. So the electromagnetic radiation is produced by dipoles, but you don't expect a dipolar radiation in gravitational wave radiation. But other than this basic difference, the propagation of the so the gravitational field will decline the way the electromagnetic fields decline. Okay, so a propagating field, the gravitational waves will travel as 1 by r square. Okay? Whereas so you will have a near field and a far field regime, and the dependence of the energy density would depend on which of these fields you are talking about. So propagating gravitational wave, the energy density which is carried will go down the way the electromagnetic wave energy goes down. So I don't know in what context he is asking the 1 by r.
So he may mean that the amplitude of the quadrupolar radiation falls off by 1 by r.
No, but the thing which is propagating will propagate with the same kind of behavior. Okay, so what I would like to know is whether he's asking about gravitational energy density or gravitational wave energy density. The two things are different.
Okay, sir. Thank you. And he had one more question, which was like, is it possible to detect gravitational waves using atomic clocks?
So see, the point is that in fact, in the case of PTA, we are using the atomic clocks because as I said, the phase residuals in the pulsar timing, the amplitude is very, very tiny. Okay. The amplitude, the characteristic strain of nanohertz gravitational wave is 1 part in 15. So it's a very small, tiny perturbation of the space-time. So if you now convert this tiny perturbation of space-time into phase residuals in pulsar timing, that comes to be around 10 to 100 nanoseconds. So the precision which you require for pulsar timing is 10 to 100 nanosecond. And to achieve that kind of precision, you need atomic clocks. So the answer to the question is yes, you need atomic clocks, but for the pulsar timing array experiment. So essentially the atomic clock would provide a reference, a very stable reference to measure the change in dimensions by the gravitational waves. And the atomic clocks do provide a very stable reference. So in that sense, yes, the answer is yes.
He is asking something like if we place two synchronized atomic clocks at like at faraway distances and a gravitational wave passes through them, will that help us detect those gravitational waves because of change in time intervals or something?
Yeah, so that's what the pulsar timing array is doing. Okay, it's not an atomic clock, but it is a clock. So that is precisely the principle of the pulsar timing array, that you have two pulsars which are in two different directions. Okay, the passing gravitational wave imprints its signature on the pulse signal or the clock signal coming from these two clocks. Okay. So yeah, if you were able to place two atomic clocks in place of two pulsars, you could actually make a very clean detection. Okay, because the pulsars do suffer from instabilities which the atomic clocks don't. Okay, but we don't have atomic clocks everywhere in the galaxy. So pulsars are the best approximation of the atomic clocks. So yes,
Okay,
the
sir.
answer is yes.
Yeah, thank you, sir.
Balchan, maybe we'll stop here. I think there were one or two questions which people wanted to ask on the experiments.
Okay.
I don't know if they're still there because the attendance has gone down quite a bit. Was it Chetna who had emailed saying that there was some query about the experiments which you wanted to ask?
Yes, sir, but we'll be discussing it in our group today. So we want a Monday slot for the discussion.